Okay, welcome everyone to this last IAMP Mathematical Physics seminar of 2021. And it's my pleasure to introduce today Christoph Schweigert, who's going to talk more about CFT correlators. And I remind everyone that this talk is being recorded and you can see the recording later on our YouTube channel. Okay, so Christoph, the floor is yours. Please go ahead.
Yeah. Thank you very much. Thank you very much for the invitation. It's good to see so many friends, at least online, but these days we are already happy if we see them online. So more about CFT correlators means that I want actually to tell you some stories which are not completely new, and then to explain how they triggered some new developments. And so actually I will start with some prehistory of CFT correlators. And as usual, if we are telling the prehistory or the history of our field, things tend to be wrong, because scientists are usually very bad at the history of their field, and I'm completely aware of that. I'm omitting many important developments if I start with a paper most of you know, because this is, some people these days think it is the starting point of conformal field theory, but it's at the end of a long development to which many people contributed. But let me take it and let me take this paper and see what's written in the abstract here. And then you see they talk about the idea, which is of course older than this paper, that in a conformal field theory, and whenever I say conformal field theory, then really I talk about two-dimensional conformal field theories, that representations, the fields are organized in terms of representations of the Virasoro algebra. Well, in terms, they are writing here irreducible representations, but maybe irreducible these days is something we are not so completely happy about, because if we want to phrase this in more modern terms, then we would probably replace the Virasoro algebra by some conformal vertex algebra. And instead of representations which can be written as a direct sum of irreducible representations, we would also allow for representations that are indecomposable but not irreducible. Now, in this talk, you don't have to know what a vertex algebra is or what a conformal vertex algebra is, but I think most of you are aware that it leads to representation of a distinguished Lie algebra of the Virasoro algebra, which is in a sense the most natural Lie algebra you can write down on integers. That's why it has been discovered before Virasoro. So again, the history is not completely correct. And it encodes conformal symmetry, and there is a certain central extension, and the central extension doesn't appear in the work of Virasoro, incidentally. So anyhow, if you look at representations, then you study the Virasoro zero mode. And if you go back to the old days, which for me is the 80s, people were looking at the case where the Virasoro zero modes acts as a semisimple operator, meaning that it can be diagonalized. So it is quite interesting to admit that L0 cannot be diagonalized. So in the simplest case, it has a Jordan form with a single of diagonal entry. So it acts on a two-dimensional space by a matrix of this type. And then we have to take into account another field, which is called the logarithmic partner. And if you go through formalism, which is reasonably standard in conformal field theory and which will not play a role in the remainder of the talk, then it leads to OPEs where both the field itself and its logarithmic partner appear. And if you have this OPE and an invariant vacuum, you can write down 2-point blocks, that's a famous exercise in most CFT books in the case where L0 acts semi-simply. It is a doable exercise in this case where you have a Jordan partner, you get a system of differential equations, which I don't want to write down completely, but you can solve it. And in the standard case, you find in most CFT textbooks, you find scaling behavior, scaling in terms of this parameter h, while in the general logarithmic case, and that explains the name, you find for the 2-point conformal blocks, again, something which looks like the scaling behavior, but you find on top of this a logarithmic term. That's why this type of conformal field theory where L0 acts in a non-diagonalizable way is also called logarithmic CFT. And
so is that action on a Hilbert space?
No.
No. Oh, okay.
But it's a very good question because if you require that the action is such that it is unitarizable for the standard involution on the Virasoro algebra, then you won't have this additional logarithmic partner. Now, it's not true that anything you have in physics necessarily requires a Hilbert space, and these logarithmic CFTs appear in the description of physical systems in statistical mechanics. So, for example, famously, if you want to describe critical percolation, then the underlying algebraic structure is a structure where L0 doesn't act on interesting representations in a diagonalizable way. And actually many more bad things happen in this percolation systems. So there are really not only mathematical reasons, but there are also very good physical reasons to study these logarithmic CFTs. And to a certain extent, since we are here among friends, one should admit that the program that was proposed in the 80s, that you should use two-dimensional CFT to understand systems of statistical mechanics, had got stuck at many, many points. And one of them is exactly this point that you should develop these logarithmic structures in much more depth, and it takes really interesting new ideas. And what I want to tell you in this talk are some ideas in this direction, and a bit more also on the semi-simple case. So what we assume here is that these representations of this algebraic structure, whatever it is, but it is not a net of observable algebras acting on a Hilbert space, that they organize in representations, and we assume that the category of representations is not necessarily semi-simple. So what I do in this talk is that for technical reasons, I impose certain finiteness conditions. And I try to eliminate a couple of technical things, keeping the conceptual aspects. So I won't be very precise about this point, but it is quite important. So informally speaking, what we assume are that the categories are such that they could be described just as abelian categories as finite dimensional representations over a finite dimensional algebra. This ensures the existence of certain things in a much easier setting than we would expect it in general. So for example, things like Liouville theory wouldn't be in the picture because Liouville theory is not finite. Well, then if you go back to the Zamolodchikov paper, you will see that they emphasize conformal blocks. They emphasize conformal blocks as in two respects. They emphasize them as building blocks of correlators, which also explains the word blocks. And they also emphasize that not in these modern words, that the category gets more structure due to structure that's inherent on conformal blocks. So for example, we've seen that the 2-point blocks have a scaling behavior, which gives rise to the structure on the category, which in the modern language would be a twist. So let me try to explain a bit how this goes, that you get a flavor of what's in the back of our mind when we start to solve algebraic problems. So they characterize conformal blocks as solutions of differential equations. And if you wish, then a vertex algebra is just a big machinery to encode conservation laws, and they lead to differential equations on the conformal blocks. This is literally copied from their paper. They get to hypergeometric equations, and very famously, such differential equations have solutions that have holonomies. And these holonomies, they are encoded. They are encoded algebraically. So in a sense, the whole business of category theory from this point of view is that you encode the structure of the holonomy of the conformal blocks in terms of tractable algebraic structure. And actually trying to compute with conformal blocks in the formulation in the mosaic papers is almost impossible. Calculating in terms of categories is relatively simple and everybody can learn it. So categories in this sense simplify. And they are indispensable if you want to talk about non-semisimple structures. So of course you can get the categories differently, and some of you know this much better than I do by considering nets of observable algebras, which then yield also braided tensor categories. You know how to encode finiteness properties there, and in such a way that you get a non-degenerate grading. In any case, you are then ending up with a very nice structure, which is a modular tensor category. So this is to be thought of as this representation category, which your favorite framework for conformal field theory provides for you. And of course, studying modular tensor categories, studying systems of conformal blocks as an algebraic geometer, studying nets of observable algebras, these are various interconnected fields where each of them is a very rich field of mathematics itself. And what I will do here is I will use structures that are constructed from a modular tensor category to encode these holonomies. And the appropriate tool to do so are symmetric monoidal functors or modular functors. And in case the situation is semisimple, such a modular functor can be upgraded. It can be upgraded to a topological field theory. This looks nice. But since I explained to you that I'm interested also in addressing the non-semi-simple case, I shouldn't insist too much on this three-dimensional aspect, because that's by now very well understood from the structure of Bordism categories, that if you want to have the extension to 3 dimensions with values in 2 vector spaces, that then you have necessarily semi-simple categories assigned to the circle. So there is a strong need to develop methods that are inherently 2-dimensional. And what I want to tell you in the last part of this talk is such a 2-dimensional method, which is new. Okay. And yeah, in any case, what these things encode are is a lot of information. In particular, they encode a lot of actions of mapping class groups. And I should insist that the mapping class group is really the fundamental group of the configuration spaces that are relevant. So that's why in the end, if we want to have single valued correlators, they should be invariants under the mapping class group. And we can deal with this question not by taking explicitly the solutions of these differential equations, but by taking these algebraic structures which encode the structure of these holonomies. Well, if you go back to the BPZ paper, then you see they give a reasoning which I wouldn't formulate in this way. Since the complete conformal group is a direct product, so string theorists would say since there are left movers and right movers, representations are in fact direct products of representations of one copy of the Virasoro algebra and another copy. So that goes under the name combining left movers and right movers, describing bulk fields. And this is a problem I want to discuss in this talk in more detail. And I want to discuss it from a modern perspective. And a modern perspective means that the field content we want to study these days is much richer indeed. So we don't want to study just bulk fields. We want to study also boundary fields, but quantum field theories should be studied on stratified spaces as well, which goes also under the name defects. So on these defects, you will have fields that change the type of defect, and you want to understand all this in one go, if possible. So if you want to understand or to construct in a certain sense these quantum field theories, these conformal field theories, you have to solve two problems. You have to determine the field content given one such reasonable combinations of left movers and right movers, and you have to determine what the correlators are to ensure their existence at least. And you'll see that I'm using here an expression, valid combination of left movers and right movers, which needs to be given some mathematical sense. And let's go back to this sense on the next slide. But before doing this, let's briefly look at these various fields we want to determine. So bulk fields, which in the case of the Ising model would be bulk fields which are chirally either the vacuum and its descendants, the spin 1/2 field, or the spin 1/16 field. And we want to determine these objects combining left movers and right movers. We want to determine them in a consistent way. We want to determine boundary fields. So in the Ising model, again, there are three boundary conditions, three conformally invariant boundary conditions, which sometimes are referred to up, down, and free. And then we want to compute partition functions. By the way, we also want to determine bulk partition functions. Well, and then you want to define disorder fields and defect fields. So disorder fields are fields where a topological defect line ends. The defect fields are fields where a topological defect line changes its type. And actually, one point which came a bit as a surprise to us is that there are many more generalizations of these fields also around, and we can describe them. So this combination of left movers and right movers, I said I have to find a valid combination of left movers and right movers. So the 20th century attempt was to compute characters of the representations of the vertex algebra or whatever chiral algebra you take, and to try to find modular invariant representations of these characters. Modular invariant representation means non-negative integers, which have the property that they commute with the representations of the modular group on the space of characters. Well, I mean, sometimes it's really bad if a program has success very early on. And I think this was true in this case, because in the first few cases for SU2, people found a classification in terms of ADE. And I mean, retrospectively, we know why the solution was so simple, because quantum dimensions are bounded between 1 and 2, and that restricts the possible mathematical structures drastically. And then this program led to some excitement that finding generalizations of ADE patterns would be a nice thing. Additional techniques have been developed, but around the mid-90s, there was a big disappointment, because it had become easy to construct partition functions which are modular invariant, but which are definitely unphysical. So in a sense, the whole program of first classify modular invariant partition function, because it's so nice to classify non-negative integers, broke down at this point. And it became obvious that most of the modular invariant combinations of characters are not partition functions. And actually, this is an example we found in during my, oh, this was far too far, my thesis work, which could be proven to be unphysical with Lie theoretic methods. So I have to apologize for scrolling through these slides. And by the way, the program would have failed sooner or later, because there was no way to use these mathematically simple-minded structures of non-negative integers to construct more general field content, and even constructing boundary fields in terms of representations of the fusion rings was a program that quickly showed to fail.
Well, what does it mean unphysical?
There can be no conformal field theory whose partition function is the partition function I'm just encircling. And why can it not be true? Because you can read off, this is the vacuum character, so you read off that the extension of the chiral algebra here is by spin 1 currents, but then it is necessarily and described by a current algebras, but embedding of current algebras, so-called conformal embeddings of affine Lie algebras, are classified, and there's nothing in the list. That's why we know that the thing is unphysical.
Thank you.
You're welcome. So let's go back to this paper one last time, and let's see what they do if they want to compute correlation functions. So here they consider associativity constraints, which I would formulate in a more modern way as follows. You want to compute 4-point correlators, and you want to express the 4-point correlators in terms of the 4-point blocks and quantities associated to the 3-point correlators, namely OPE coefficients. So this means that if you take a 4-punctured sphere and you punch it, you do factorization, the correlators have to be related. They have to be related in a way which takes into account that you go from S channel to T channel. So really in this equation, I copied literally from the paper, they suppressed 6J symbols. But anyhow, they were able in this paper in specific models to come up with solutions. So what I take here is that correlators should be specific conformal blocks, specific elements in these conformal blocks, vector bundles, which I describe in terms of their holonomies by means of a modular functor, which should be invariant under the mapping class group and compatible with factorization. And now I've translated this problem into a problem that can be investigated in really full mathematical detail using a well-established framework. And the very gratifying thing is that this problem turns out to have nice answers in general and even more general frameworks. And I want to tell you a bit about this story in the remainder of the talk. So that's the problem I want to address. Before I address it, I go back to some prehistory, which is now almost 20 years ago. Since it is about determining specific vectors in conformal blocks, and a three-dimensional TFT allows to address to specify specific vectors on conformal blocks on the boundary in terms of three manifolds with boundaries, there was an approach that we developed back then where we used three manifolds with boundaries. I think that the approach had some important successes, but you have to keep in mind that it uses three manifolds, and three manifolds are linked to semi-simplicity. So if you want to go to logarithmic CFTs, you have to think about other tools. And that's what this talk is about. And the second reason is that while we could come up with a very precise description of the multiplicities of bulk fields, the precise analysis of these bulk fields is pretty involved. It's so involved that I'm not going to explain to you in detail what this bulk field is. So I wrote here even that the formula is not very enlightening. And it is a formula which cannot be generalized in terms of left movers and right movers beyond semi-simplicity, because then there's no reason why you should be able to write everything as an external tensor product of representations of the left movers and representations of the right movers. So this type of expression definitely needs more insight and it needs more machinery. And I want to give you the remaining half of the talk some flavor of this. So before doing so, let's go back to two old papers. So what we actually get if we look at this type of factorization constraints is that we should be able to form four-point correlators in a consistent way. And in order to do so, it is very famous that you shouldn't look just for algebras and products, but that really the algebras you have are Forbinos algebras. So this is in a different disguise, the statement that you shouldn't forget about the non-degeneracy of the two-point functions, because the non-degeneracy of the two-point function will induce on these bulk objects a non-degenerate bilinear form, and that's the hallmark of a Forbinos algebra. And if I'm saying Forbinos algebra, I really mean symmetric Forbinos algebras, and I will not explain what symmetric means here, but if you're asking me, I will be happy to explain this. So these field objects due to the OPE are algebras, but due to the non-degenerate bilinear pairing are Forbinos algebras. So we should be able to come up in this general category theoretic setting with lots of Forbinos algebras. And actually, this is possible. And so now just to prepare you mentally for the talk, the remainder of the talk, coming up with these Forbinos algebras uses some a certain amount of theory that has been developed by several authors in the last 10 years. I will then use these Forbinos algebras in a particularly simple instance in the last part of the talk, and then there will be less technical background. I will allude to less technical background. So the route we are going to take is a bit uneven, so it's not that the steepest part is at the end. So actually, I have to expose you to one piece of category theory, namely, if you think about supervector spaces are the two graded vector spaces. What are morphisms of supervector spaces? Well, these are grade preserving linear maps. Grade preserving linear maps means if you write them down in terms of matrices, then there is something which goes from grade 0 to grade 0, something which goes from grade 1 to grade 1, and then there are no things that change the grade. Now, if you look into books on super geometry, or there are not so many books on super algebra, then you see that people also look at matrices where also the grade changing entries appear. And you say, why shouldn't I admit grade changing homomorphisms? Well, the point is, if you think in a clear categorical way, these are really the home spaces in the category, but any monoidal category has also a notion which is called the internal home. And the internal home and the home are not the same thing. So the home is what you put into the category from the very beginning. And in the case of supervector spaces, it is these are the grade preserving maps. But then, you know, you can take a tensor product of supervector spaces. And if I take a tensor product of supervector spaces, then I can wonder if I'm studying the tensor product of two supervector spaces and the homes, which are grade preserving homes. Well, if I want to express them in the following way as the home from a single supervector space into an object which is a supervector space, well, then you can compute what this thing should be. And obviously, the thing will have odd components and even components. And that's actually, if you write V as and W as some R or C and M, this is the space of matrices which have also off-diagonal elements. So everybody who has done a little bit of calculations using supersymmetry has worked with internal homes. And internal homes work actually in a slightly more general setting. And probably I won't even explain in too much detail how this setting looks like. But one idea I want to expand on is that internal homes can behave well even if homes do not behave well. And that's what we are going to use for CFT constructions. Well, just as an aside, the setting in which we are really using this is the following one. If you have a monoidal category, this is, you have a tensor product, and the tensor product, well, think about a monoidal category like a ring in the world or an algebra in the world of categories. If you're studying algebras, you will very quickly also start study modules over the algebra. And the same is done in categories. And there is the notion of a module category. And here we have a mixed tensor product where we take an object in the monoidal category, an object in the module category, and we produce an object in the module category. That's really the setting in which I'm secretly working. Now, in this setting, you can set up something that's well known from modern representation theory. You can set up Serre functors. Well, if I wouldn't write here at this point the inner Hom, but just the Hom, then these are ordinary Serre functors. And writing Serre functors for a category is a pretty dull thing. It's not interesting because the Hom functor is left exact. The dual of the Hom functor is right exact. So if they are equal, they are exact, but the Hom functor is exact for precisely if the category is semi-simple. I'm just telling you this and to show that, to explain why Serre functors for algebraic geometers are used in the setting of derived categories. Here we are doing something completely different in a sense. So we require the same thing that defines a Serre functor, but we do it for the inner Hom, not for the Hom. And then the thing exists. The thing exists for sufficiently nice module categories, which exist over non-semi-simple categories. So somehow the module category is relatively non-semi-simple. That's a very interesting situation. And you can develop a complete theory. And this is, of course, for the specialists. And I'm not going to tell you many details. What I'm going to tell you is that also the relative Serre functors are related to Nakayama functors. And indeed, the Serre functors in algebraic geometry are actually derived functors of Nakayama functors. So there is a very nice story which has its own mathematical value. And now, if you go to algebraic geometry, then people will tell you it's interesting to look at situations where the Serre functor is trivial. Well, that's essentially what happens for Calabial varieties. And that's why Calabial varieties are one reason why Calabial varieties are interesting. So what do we mean if our Serre functor is trivial? Well, we mean that it is the identity functor, but in a very strong way. And I'm dropping here a certain amount of technicalities. In a very strong way means that it is compatible with the action of the monoidal category. And there are subtleties because the action is twisted by biduals and you have to trivialize the biduals and all this stuff.
Excuse me, would it be possible to explain the notion of a Serre functor?
Sure.
I just checked that there is no Wikipedia article on Serre functor.
Okay, I wasn't aware of this, but for the moment, I'm just concluding that I didn't learn it from Wikipedia. But let me explain this. So a Serre functor is an endofunctor of a category, which has the property that if I'm looking at Hom, M, and dual, that's and in order to make sense of this, I should say that this is a linear category. So the Hom spaces are vector spaces. I don't want to get problems with taking the vector space duals. So I assume that all Hom spaces are finite dimensional. That's necessary here in this setting. And then I take the dual of the Hom functor, and I want this to be equal to the Hom functor. Now, this would taking covariant and contravariants of the arguments into account, you would require that these two things are functorially isomorphic. And in general, you can require this, but it's also interesting to ask that this holds only up to applying some functor on this argument. And this functor S here, that's the Serre functor.
Thank you.
Yeah, And what we do is we take almost the same definition, but we replace it by the inner Hom, the internal Hom. And since the internal Hom is an object in a monoidal category, we replace the vector space dual by the dual in this rigid monoidal category. Or actually, we could also write here a co-Hom, but that's more for the experts. So we trivialize these Serre functors in the sense that they should be the identity in a sufficiently strong way. And then you get very pleasant surprises. This is a Calabial-type condition. And this Calabial-type condition implies that the inner Homs are in fact Forbinos algebras. So from a Calabial-type condition, we can produce, well, an inner end, like any decent end, is an algebra. And from this additional Calabial-type condition or trivialization, we can obtain the structure of a Forbinos algebra. So we are closer to having a systematic supply of Forbinos algebras. And I was saying Calabial-type condition, indeed, if the category is indecomposable in a certain sense, then the pivotal structure is unique up to a scalar. So by a slight abuse of language, I was saying it is a condition and not a structure, and the scalar actually isn't very relevant.
And what does it mean, pivotal?
Pivotal means that the bidual is trivial. So you see that here, if the bidual wouldn't be here at this point, then this would be a functor which behaves like a morphism of modules because the C can travel outside. This is not completely true for the Serre functor. There's a very important twist to the story, which is that here you find a bidual, and what we assume is that the bidual on the category is trivialized, is trivial. And this is in particular true for all modular tensor categories. And these are the categories you find, for example, for finite nets of observable algebras as well. So it is structure we have naturally in the game for chiral CFT. Okay, so now I need a bit more. I need also Forbinos algebras in the Drinfeld center. And there is a technical twist in the story, namely, from the CFT perspective, you would like to work with a combination of left movers and right movers. And the non-degeneracy of the braiding can be shown to be equivalent to the statement that this combination in which the bulk object combining left movers and right movers will live is equivalent as a braided monoidal category to the Drinfeld center. And there's an extensive technology for the Drinfeld center. And if you go through this technology, then you will be able to produce Forbinos algebras. You will be able to produce Forbinos algebras also in the Drinfeld center. And we do this in a very logical way. We look for a module category over the Drinfeld center. And you have to prove a couple of things, and these are actually not easy proofs, but you can show that this category of module functors over the Drinfeld center is under the conditions that hold in a CFT. It is a pivotal C module category, so that the inner Homs of this category are Forbinos algebras in the Drinfeld center.
Excuse me, what is the Drinfeld center?
The Drinfeld center is defined as follows. Whenever you have a monoidal category C, there is a canonical way to turn it into a braided category. And how do you turn it into a braided category? You say there is a new category where the objects are pairs of consisting of objects in the monoidal category and so-called half braidings. So a half braiding means that I have a systematic way to change the order in the tensor product with V0 for any V. And a systematic way means it is functorial and it obeys a hexagon axiom.
Mm-hmm.
So we don't want to go beyond the hexagon axiom, of course. And so these objects form a braided monoidal category, and that's what's called the Drinfeld center. And for reasons which go beyond this talk, the important thing is that if I take the category in which left and right movers live, it is canonically equivalent as a braided monoidal category to the Drinfeld center.
Yeah, so a braided category has only a half braiding and not braiding?
No, a braided category has a braiding. What I'm claiming is that if I take the category whose objects are objects in C plus a half braiding, then the category of these objects turns out to be braided. This is something you have to show.
Okay.
Yeah, and a braided category has a braiding, and you can use the half braiding to construct a braiding.
Okay, thank you.
You're welcome. So in this way, we have a supply of symmetric Forbinos algebras in the category Z of C, which is equivalent to the category in which we are looking for bulk objects. And notice I'm nowhere using decompositions of objects into direct sums. I'm really working with genuinely category theoretic concepts, which are very sound objects which have a wide range of applicability. That's the point of this program. And so now I have enough symmetric Forbinos algebras, and now we can build up in principle the field content of a local two-dimensional CFT. So actually the boundary conditions will be objects in an exact pivotal module category. The boundary fields will be the internal homes. So by our theorem, they are automatically Forbinos, and the OPEs are the composition homomorphisms of inner homes. And so to go from boundary to bulk is also something which goes in natural category theoretic structures. So it goes by taking these inner homes, which are now objects in Z of C. And you have to do a bit of work to understand these things. And actually the work took us about 5 years, but well, what you can see is that these are actually really generalizations of the bulk objects we were writing down earlier on, and that these objects have a very nice interpretation in terms of coends. So coends are, or here I've written the formula in terms of ends. Ends are generalizations of direct products, very roughly speaking. And ends come with structure morphism. And what you get from these structure morphisms is something we urgently want. The structure morphisms we gain from these mathematical results are candidates for bulk boundary OPEs. And now we are in a very good shape, because if we look at Levelin's old paper about CFTs with bulk and boundary fields, we have solved in this setting automatically quite a few things. So what we have solved is this here, because we have Forbinos algebras in the bulk. We have also Forbinos algebras on the boundary. Now, if you look at this here, if I had explained what an end is, an end comes with a structure morphism. The structure morphism is a dinatural transformation. This is just the dinaturality of the end. You get it from the previous result. You get this consistency constraint for free, and this result can be proven. So all genus zero consistency results follow from this answer. Requirements follow from this answers. What we are unable to show in this context is genus 1, which is modular invariance of one-point functions on the torus, and the so-called Cardic constraint. So for this, you need new techniques. And at the moment, we are about to build up these techniques. And the techniques are ready by now for the semi-simple case, but there is work to be done for the non-semi-simple case. And this is what I want to show you in the last 10 minutes. And so here, just because I'm giving this talk in 2021 and not in 2025, we are restricted to the semi-simple setting, but there are, of course, ideas how this should work in general. And so let's do something which is seemingly unrelated. These are stringnet models. They come actually from solid state physics, and they are also called Levin-Venn stringnet models. So let's take an oriented smooth surface. It can have boundary circles. So you see that here, I've drawn boundary circle, and we draw a finite graph on this surface. And now we color this graph given a spherical fusion category. And if you don't want to know what spherical fusion means, just take a monoidal category. And we color them in such a way that the edges are colored with objects and the vertices with morphisms. And spherical fusion are properties which ensure that the sentences make mathematical sense. The sentences I said. Now you do something very crude. You consider simply the set of all graphs with a given boundary value if you have boundaries. You generate a vector space, which is, of course, not only infinite dimensional, but not even countably dimensional. Yeah. And then you do something which these Levin and Venn invented, namely, you impose local relations by taking a disk, and whenever two graphs evaluate to the same on a disk, then you identify them. So you're constructing a very big quotient. And this construction is actually, although it comes from solid state physics, it's perfectly mathematically rigorous by now. And it turns out that this realizes a modular functor. In particular, since the mapping class group acts on the graphs, these spaces are representations of the mapping class group. And whenever I'm drawing a graph on a surface, I'm getting a vector in this so-called stringnet space. And this is really what we want to do. We want to identify vectors in these vector spaces because they turn out to be canonically isomorphic to vector spaces in a 3-to-1 TFT. And here we can really identify vectors not by taking the boundary of a three-manifold, because three-manifolds are bad for non-semi-simple categories, but by drawing graphs on surfaces. And drawing graphs on surfaces is very intuitive, very geometric. So, of course, you have to do more work than we want to do so shortly before Christmas. You have to work out, for example, how to deal with boundaries. Actually, it leads very naturally to the cylinder category. And I think many of you have come across the idea of Vaughan Jones now I missed the word, the tube algebra. Yeah, so about tube algebras. Really, this is the tube algebra in a slightly more categorical setting. Yeah, and the tube is the cylinder. And so using this description of boundary values, we can describe now the bulk objects and the boundary objects in a very nice way as objects in the Drinfeld center. And I'm cutting a bit things short. So if I want to describe now, for example, a defect field, which changes a topological defect F into a topological defect G, and this could be here two different CFTs. This could be here, for example, something in the A series and something in the D series. Then what we do is we translate these data into special symmetric Forbinos algebras. We translate the data here into bimodules, and then we write down a specific element in a tube algebra. That's the tube, that's the ingoing circle, that's the outgoing circle. And we have an element in the tube algebra, which is actually an idempotent. And remember from Jones's work that the blocks in the tube algebra are simple objects in the Drinfeld center. Here the objects are not simple, but these are exactly in the semi-simple case, these relative natural transformations we had constructed earlier on. And now things become amazingly simple, although working it out takes a bit of time. So you can even go to the situation where such defects, these are topological defects, 4 of them meet, and they separate 4 different pairings of left and right movers of the same left and right movers. So if you have several modular invariant, and you can write down exactly what the field content is at this point in terms of this projector in the tube algebra. And now we craft this projector at the right place. We endow anything else with enough Forbinos algebra lines, and we get a stringnet. A stringnet determines a vector in the vector space of conformal blocks. And now you are in business, you're sitting down, you are proving things, and you show that these elements obey factorizations and are invariants of the mapping class group. So just by using these geometric tools, we have a very good handle to address also the correlators in higher genus in a purely two-dimensional setting, which is, by the way, enormously convenient for a person like me who has big problems to imagine anything in a general three-manifold and to do surgery in a three-manifold. If you haven't been trained as a topologist, it's really painful. So what we need to develop is stringnets beyond semi-simplicity. And obviously there are ideas for this around. I should say that I slipped the word rigid and duals here in this talk. It it would have been a completely different topic of a talk to explain that in general, if you go to non-semisimple CFTs, the representation categories are not rigid. They have a more general structure. They have the structure of a so-called Grothendieck-Verdier duality. But this Grothendieck-Verdier duality is, again, amazingly friendly to stringnet models, and using at least at the moment, two very smart postdocs have managed to construct 4 Grothendieck-Verdier categories, not modular functors, but at least more, because a modular functor has a representation of the mapping class group, they have managed at least to construct representations of the handle body group. So we are pretty close to mapping class groups. And I should also add that these stringnet models are, have another advantage. They, so people in the tensor network community, they have worked out many, many approximation schemes. And the way we obtain the correlators is friendly to approximation schemes of this type. And this is really one of the big funds we had in the last 2 years. We started to talk to solid state physicists actually in Ghent. And so 20 years ago, I couldn't have imagined that you can talk to solid state physicists using the word spherical fusion categories and without explaining it. Now you find these people. And I think this is a field where we can expect many pleasant surprises for mathematical physics, and conformal field theory will stay part of this kind of pleasant surprises. I'm pretty sure about this. So thank you very much for your attention.
Thank you. Thank you very much, Christoph, for this nice talk. Are there any questions? So please go ahead and unmute yourself. Yes.
May I? So you mentioned a 2x2 Jordan block. So
yes.
Do you also want to explain larger Jordan blocks, or do they appear in CFT?
Yes, they appear, and you actually find arbitrary big Jordan blocks. I wrote 2x2 because then these equations which generalize the scaling behaviors become still tractable, and I can give reasonably honest equations on a short slide.
Mm-hmm. Okay, so you mentioned the relationship to the hypergeometric equation, to the Riemann equation. Now, in the Riemann equation, you sometimes also have logarithmic solutions, and is it related to these logarithmic CFTs?
Yes, and actually that's a good point where the semisimple categories are, in a sense, more difficult than the non-semisimple ones. If you write down these hypergeometric equations, even for the non-semisimple, for the semisimple categories, you will find a space of solutions that has logarithms, because that's how generally it is. And you have to eliminate them in the semisimple case, well, more or less not by hand, but by looking carefully what additional constraints you have. And in the non-semisimple case, there's simply no reason why you should eliminate them.
Yeah, I mean, often they are more important than the semi-simple cases. The important, the Legendre functions, for instance, are related to logarithmic situations.
I completely agree, and Of course, then we very quickly translate this into an algebraic problem because that's the type of tools we are using. But these logarithmic partners, they contain a lot of interesting information. And they contain also quite a few challenges in representation theory, because there are really crazy things going on which aren't really completely understood. If you have, I should take a different pen. If you take a character, then in whatever kind of representation, you take a trace, a sum over the diagonal elements. Now let's assume that you're now looking at a matrix which has a block diagonal form. Then it turns out that the sum, there's in this logarithmic CFTs, there are situations where you should take the sum over the diagonal of this block. Of course, nobody who got a decent course in linear algebra would dare to do this. There's no reason why this sum should be independent of the choice of basis. Still, if you set up two bases in a specific way, you get things which are almost canonical and which are complements in the space of one-point functions complementing the characters. Yeah, so it's well known that for non-semisimple representation categories, the characters do not span all class functions. And these are the complements. And it's completely unreasonable why this works. So I talked about this to representation theorists working on finite groups, because I thought they should have encountered this if they work in characteristics dividing the order of the group. But there are many of these things hidden in this logarithmic partners, because this is really very strongly related to the one-point function of this logarithmic partner. So I completely agree that they are frequently the more interesting ones.
And so could you name the simplest example of a logarithmic CFT? I mean,
Well, probably if you are asking me about the simplest class of logarithmic CFTs, then this is the W1P models. And if I should explain them to you, then let me do this as follows. If you look at Virasoro minimal models, there's something called Katz tables. So for example, for the Ising model, you will find a Katz table which has 6 entries, but every field appears twice. So it will be as follows. If you weaken the condition on the representations, then you will typically add to the Katz table one more row and one more column, plus additional identifications. It turns out that here in this case, you are adding one more row and one more column to just nothing. So it's a bit degenerate. But these are the simplest these are extending the minimal models in this way are the simplest logarithmic CFTs. And if you want to relate it to a system that's known to almost everybody, if you do it for W2, 3, then this is the chiral symmetry that's relevant for critical percolation. This has Virasoro central charge 0. This is the symmetry that effectively Cardi has used in his famous work where he computed the crossing probability for percolation problems. So this would be the simplest examples. But simple doesn't mean that it is easy to treat it, and in particular this percolation problem. This is something where the underlying category is not rigid. So that's something where you really have to work in much more generality, and where we are still pretty far away. So the promise that two-dimensional CFT can elucidate statistical mechanics that was very frequently put forward in the 80s is something that, in my opinion, the promise hasn't been realized today. It still needs lots of work.
And Liouville theory is not logarithmic.
Liouville theory is a bit even more general, because in what we consider, I said very briefly in the beginning, I have some finiteness conditions.
Yeah.
And here I mean, for example, that there are only finitely many simples. And Liouville theory has infinitely many simple representations and even a continuum of them. And if you want to write down bulk fields in Liouville theory, they are typically written down in terms of integrals. So people will talk about some integral density and then write down some integral over Hilbert spaces, which can be given as a meaning in Hilbert spaces because there's a direct integral of Hilbert spaces. And that will be a bulk object. But for the moment, the interface of functional analysis and category theoretic structures is not so far developed that we could make a direct contact between these methods. But there is a bit of hope because from a very surprising side, people in linear logic, they are increasingly developing category theoretic structures in functional analysis for reasons which I, to be honest, can rather guess than understand. Yes, but I learned a few things in this direction, for example, from Paul-André. But I'm not sure this will be incorporated in CFT before I'm retired.
So just to follow up quickly, does it have something to do with some monoidal structures? Is this like where's the functional analysis?
Well, the functional analysis is if you want to make sense of an integral over P.
Okay, so this is where this is needed.
Yes.
Okay.
And then you know that if you have a family of Hilbert spaces, then you have a direct integral of Hilbert spaces. That's probably Gelfand-Naimark, and you will remember the volume better than I do.
Yeah.
And then you can make sense of such a direct integral.
Yeah.
The problem is that, as you know, once you go to the world of Hilbert spaces, then the tensor product becomes very nasty because the tensor product of Hilbert spaces is not a categorical Hilbert space, categorical tensor product. Yeah. So
yeah, that's where where the bodies are.
In a very monoidal spirit. Yeah. I'm afraid to touch Hilbert spaces.
No, that's right. So this is why I guess that's why it's relevant for these people in logic. Maybe they also have some sort of tensor products that they care about.
Oh yes, the tensor product in logic is actually the linear generalization of end. And then in these Coten-Quartier structures, there is a second tensor product, and that's the linear generalization of OR. Because all of you've worked with a monoidal category in the very first week at university, but they didn't tell you, right?
Yes. Well, that's unfair.
Yes, because if you take the category where the objects are subsets of a given set, yeah, then you have two monoidal structures. One is union. And of course, union with empty set is the same set. So that's a monoidal unit. And the other tensor product is intersection.
Right.
And intersection, what is the unit? Well, that's the set itself, right? So there are two, set theory has two tensor products with two different monoidal units, but they are related by negation. And that's where the logic people are interested in. Yeah. And and the negation is, of course, a duality. And that's why we can learn from them about duality. And that's why they are using Grothendieck-Poitier structures to describe dualities.
That's really cool. Yes. I think I have an idea how to make my first year tutorials a bit more interesting next year.
Yes. And it's a unique selling point for a British university who's selling its services.
All right. Any more questions?
What is a 3-to-1 topological field theory? Does it so is it a three-dimensional theory with two-dimensional defects and one-dimensional something, or?
Well, if you go back to Siegel's axioms of or Atiyah-Siegel's axioms of a topological field theory, then you have a category where you have d-dimensional manifold, d-1 dimensional manifolds as objects, and Bordisms which are d-manifolds as morphisms. And that's what I would, and that's represented on vector spaces. So to a d-1 manifold, we associate a vector space to a cobordism, a linear map. That's what I would call a 3-2 TFT if D is equal to 3. Now, we want to do something which is slightly richer and which allows on our d-1 dimensional manifold, which allows that ribbon graphs end. But these ending ribbon graphs, they are really better formalized as boundary circles. So what we have is now a TFT where 3 manifolds, 2 manifolds, and 1 manifolds appear. That's the 3-to-1. So we are in a bicategorical setting, to be precise, where the objects are circles or disjoint unions of circles. The 1 morphisms are surfaces, and the 3 morphisms are 3 manifolds with boundaries.
Thank you.
Yeah, put differently, this has been done, of course, before in a different language. All the time, people have been looking not just at 3 manifolds, but 3 manifolds with Wilson lines. And that means that there has been inside the 3 manifold also a one-dimensional structure. And that's what we are reminded about. And that's what the terminology has changed. The true thing behind it hasn't too much changed.
Okay, any more questions? Okay, I think we had a fair amount of discussion. So let's thank Christoph again for this nice talk.